So when we convert from ratio to angle, we usually use our calculator to do that, to be able to go from an angle description of that position to a ratio description of that position. We need to usually use our calculator. However, we want to avoid doing that when we don't have to. And there's two situations where we don't have to. In fact, you'll be required to do this without a calculator, is when we have a 30-60 triangle or 45-45 triangle. And because of the symmetry that the 30-60 triangle comes from, is basically half of an equilateral triangle, we know that these three triangle sides are the same, so that means the base is going to be exactly half of this length. And we can also calculate the exact value of the vertical component here using Pythagoras. With the 45-degree angle, we know that the symmetry is exactly half a square. Okay, well, we know that if we split a square in half there, those angles are going to be 45 degrees. And we know that all four sides of that square are going to have equal length. And knowing two lengths of that square side, we can calculate the diagonal length, which is square root 2 using Pythagoras. Now these, if you remember where the shapes that they come from, it is easier to memorize these ratios. But you do need to memorize these ratios. And not only that, we're going to have to find all these special angles in the circle now, since we're doing circle trig. So when we talk about these special ratios and special angles, we need to use exact values, not just for the side lengths, but for everything, from going from angle to side length as well. So for example, here's 210. If I draw 210, 210 is in this position right here. Okay, there's 210 degrees in standard position. Now the triangle that's associated with this happens to be a special angle. Okay, because the reference angle here is 30 degrees. That's 90 degrees, so this makes it a 30, 60, 90 triangle. And to be able to find the trig values for this, we don't use our calculator. Although a calculator gives us the same decimal values, we're going to keep it in exact values. So for example, cosine of theta then works out to be, well, cosine, this triangle is going to have -1 to -√3. Okay, when I relate it to this triangle here. And again, make sure that, I'm just going to highlight this, we are dealing with positioning. So to the left √3 and down 1 is different than up 1 or right √3. So that's really important when we talk about the ratios. So the cosine ratio becomes -√3/2. The sine ratio then becomes -1/2. Okay, so it's no longer just a triangle, because if we're talking about the positive values, we're talking about just in quadrant 1. We are not in quadrant 1 anymore, and we need to distinguish this position from the quadrant 1 triangle. The tan ratio is going to be the slope. The slope is positive because it's going up like that. Okay, it's going to be -√3/-1, which simplifies to +√3. And the reference angle that refers the shape of the triangle is going to be our 30-degree angle. And the reference triangle is always made with the x-axis. Okay, although there's a similar triangle that we can make here along the y-axis, we don't ever use that one. We always make our reference triangles with the y-axis, the x-axis. We always drop from the point vertical line either down or up to the x-axis. So here we have a point defined by √3 and -1. So √3/-1 is right about here, and defines that position right here. Now I could use my tan ratio to work out the angle. However, these are exact ratios. This ratio of √3 along this side and 1 to this side is a special triangle. So we want to be able to use our special angles and not have to use our calculator to do this. So when we write the trig ratios, okay, the cos ratio is going to be positive root 3 over 2. The sine ratio is negative 1 over 2, and again the negative is important. And the tan ratio has negative slope. It's going to be negative 1 over positive root 3. And the exact angle position can then be worked out, because we know that that's a 30-degree angle in here, okay, in the reference angle. Okay, but remember that theta is always measured from 0, 0 going positive in this direction, or negative in this direction. Well, I'm just going to say that's negative 30 degrees. So I went in that direction. Now I could describe the exact same angle going around in the positive direction, and theta could also be described as 330 degrees in the positive. And these two angles are the same position, so they are called coterminal angles. Okay, so the last one here, we want to work out the vertices of this triangle. So I'm going to start with the easy one here. So this one here, that position here is going to be 0, and let's say that this radius is 1. Okay, so that position there is pretty straightforward. We go 0 to left, 1 up. This one here, we've got to go get to that position. Now we want to figure out what is the left and vertical component. And if I draw in that triangle, you can see that that is my special triangle here. And my special triangle, instead of having a radius of 2, is now going to have a radius of 1. So relating it to I'm going to just draw out my triangle here. This is going to be 2, root 3, and 1. So what are the coordinates going to be here? This is going to be negative root 3. Negative root 3 is a long side. Negative 1 is a short side. Okay, but now this has to be divided by 2. Okay, so because this triangle is half the size of this one here, we need to have negative root 3 and 2, and negative 1/2. So the coordinates are going to be negative root 3 over 2 is my x, negative 1 is my y. This one here is symmetrical, so we can see that if we draw in the triangle here again, we could see that it's the same. But now instead of going negative root 3 over 2, we're going to go positive direction in the x, okay, because this is a different position. And we're going to go down, oops, that's going to be negative 1/2. We're going to go down still, so it's still going to be negative or down 1/2. So we do need to remember that this is about positioning, so we have to figure out the left, the horizontal, and the vertical positioning. So it's good to draw that little reference triangle. We're relating it to special angles, so their special angles are going to be our two triangles here, okay, our 30-60 and our 45-45 triangles. So those are important that we recognize those triangles, recognize the ratios, and be able to relate it to the angles in this circle. Okay, so in this case here, this would be 210 degrees if we had to find that. This angle here would be 330 degrees in standard position.